Hello friends, in this short lecture we will learn basics of refrigeration. After completing this lecture you should be able to answer that what do you mean by refrigeration? How second law of thermodynamics and refrigeration effect are related? How do we evaluate performance of a refrigeration system, or what do you mean by coefficient of performance? You should also be able to know that what are the different types of refrigeration systems which are used around the world. What is refrigeration? Refrigeration implies cooling of some closed space. For example, this box, which is representing a space which requires some cooling. To cool it down, we need to remove some amount of heat Q from this space. That will decrease the temperature of the space. But what will happen? The temperature would be lower than its surrounding. Due to this temperature difference, some heat would leak into this space from its immediate surrounding, and if this Q amount of heat which is getting into this space, cooled space, if not removed, then it will increase the temperature of this space, and hence it will not remain cool anymore. So Q amount of heat need to be removed continuously, because this heat leakage will be happening all the times whenever this space would have some interaction with its surrounding. To remove this heat continuously, we use a system called refrigerator, and this setup can continuously remove the heat from this space. But in accordance to the second law of thermodynamics, heat cannot be removed from low temperature body without the aid of some external agency. So this refrigeration system would require some amount of work W, with the help of which it can remove Q amount of heat from the space which is to be cooled, and this total energy Q plus W will be rejected to the surroundings. So a system that continuously removes the required amount of heat from the designated space is called refrigeration system. Second law of thermodynamics and refrigeration. These two things are interrelated. How? The second law of thermodynamics states that heat cannot flow from low temperature body to high temperature body without the aid of an external agency. Say for example, you have a low temperature body having a very low temperature represented as T minimum, and you want to remove Q1 amount of heat from this body, and you want it to be rejected to high temperature body which is at T max. And we know we require a refrigeration system to carry out this task, but in accordance to second law of thermodynamics, you require W amount of work to have this effect happening, and this way this refrigeration system will reject Q2 amount of heat to high temperature body. So first law states that the energy Q1 which is entering into this refrigeration system and another energy W which is entering into the refrigeration system would be equal to Q2, which is the energy rejected by this refrigeration system. Coefficient of performance. Since we have already seen that in a refrigeration system we need to give some input in order to get refrigeration effect. So here we need to know that how well the refrigeration system is working. To evaluate how well a refrigeration system works, we use a performance index which is known as coefficient of performance. A coefficient of performance is a ratio of desirable output to the input. In case of refrigerator, the desirable effect is the refrigeration effect and the input is work. So COP of a refrigerator is written as Q1 upon W. On the other hand, we also see that Q2 amount of heat is rejected by the refrigeration system, but it is supplied to a high temperature body. Suppose our purpose is to heat up this high temperature body. If we want to maintain this high temperature of this high temperature body, we need to supply Q2 amount of heat to it. So if our desirable effect is supplying heat, then the same system will be called as heat pump, not a refrigerator. So the COP of a heat pump would be defined as heating effect divided by work input. So it is equal to Q2 divided by W. And with some manipulation, we can see that COP of our heat pump is always greater than 1 because it is equal to 1 plus COP of refrigerator. Units of cooling capacity of refrigeration systems. Cooling capacity is the rate with which a refrigeration system removes heat from the cooling space. Usually, it is expressed in terms of tons of refrigeration. Tons of refrigeration is defined as the capacity of a refrigeration system which can freeze 1 ton of liquid water at 0 degree centigrade into ice at 0 degree centigrade in 24 hours. And if it happens by that system, its cooling capacity would be 1 ton. So 1 ton of refrigeration is also equal to 211 kilojoule per minute or 3.5 kilowatt. In industrial world, mostly the refrigeration systems, the capacity of refrigeration system is expressed in terms of tonnage. There are different types of refrigeration systems by which we can have this refrigeration effect. The first one, which is most widely used, is called vapor compression cycle. The second one is gas compression cycle. Third one is absorption cycle, and the fourth one is thermoelectric refrigeration. Vapor compression cycle is the cycle in which we use a refrigerant which alternatively be in vapor phase and in liquid phase. The vapor phase of refrigerant is compressed, then it is condensed, and later it is expanded and then vaporized. But in case of gas compression cycle, the refrigerant is a gas that remains always in gaseous phase. It does not change into vapor or liquid phase. Absorption cycle involves a refrigerant which is mixed into liquid and then it is compressed. thermoelectric refrigeration system involves passage of current through two dissimilar metal wires. Here we will learn that how vapor compression cycle works. This cycle basically involves four basic elements or components. The first one is a compressor, the second one is a condenser, followed by expansion valve and evaporator. These four components are connected to each other in series. A compressor uses piston cylinder arrangement as shown in this figure, where at one refrigerant in vapor phase enters into the cylinder, and with the help of the piston it is compressed isentropically, and for this compression it requires some amount of work. So you can see that W in is getting into the system. With the help of work input, the refrigerant is compressed up to state 2. So 1 to 2 it is compression process and carried out isentropically. Isentropically means reversible adiabatic process, where the refrigerant does not exchange any heat with its surrounding. At 2 state, the refrigerant would enter into condenser. At the condenser inlet, the pressure and temperature of the refrigerant are very high, because the work energy which was consumed to compress the refrigerant vapor was converted into internal energy, and it raised its pressure and temperature both at very high level. At this high pressure and temperature, the refrigerant vapor enters the condenser, and in condenser, since the temperature of the vapor is so high, even it is higher than the temperature of the environment. So because of this temperature difference, the heat QH is rejected to the environment, and the condenser, as the name implies, condenses the vapor of the refrigerant ultimately into liquid phase. So at state 3 we get saturated liquid of the refrigerant, and that is at high pressure. Since this heat rejection process in the condenser does not observe any pressure loss in ideal case, so the process from 2 to 3 was constant pressure heat rejection process. So at 3 the pressure is high, temperature is still higher. After this 3 point, the refrigerant in liquid phase would enter into the expansion valve, where with the help of expansion cylinder or capillary tube, the high pressure refrigerant is expanded up to very low pressure. Since in this expansion process throttling would happen, that will get the pressure at the outlet of this expansion valve to be very low, as well as the temperature of the refrigerant will also become very low. It is so low that it will provide some cooling effect when it is supplied to the evaporator. Evaporator is nothing but the space where we require refrigeration effect. So here the very low temperature liquid refrigerant which is flowing inside the tubes of the evaporator will absorb the heat from its immediate space and will give cooling effect, and after absorbing the heat the liquid refrigerant will get transformed into vapor phase, and finally at point 1, state 1, it will be saturated vapor, and the cycle repeats. In this whole cycle we can see that with the help of work in, that is W in, the heat from evaporator is rejected finally in the condenser. Vapor compression cycle can also be shown in this figure on TS diagram. In TS diagram we see a dome type curve. Of this dome type curve, the left hand line shows saturated liquid line, and the right hand curved line shows saturated vapor line. Both are meeting on the peak of this curve, which is known as critical point. We can see that this compression process which was carried out inside the compressor is represented here by 1 to 2 line, which is an isentropic line, because on x-axis we have entropy S and on y-axis we have temperature T, and we can see that how temperature is increasing during this compression process. Not only temperature, it is pressure which is also increasing. So the pressure at point 2 is very high. Now 2 to 3 is the process carried out inside the condenser, and we can see that the temperature is decreasing, but this line is a constant pressure line, so from 2 to 3 pressure remains constant. At point 3 we see the 3 point is lying on saturated liquid line, so the refrigerant has become liquid refrigerant at point 3, and at 3 point it enters into the expansion valve, where it expanded using throttling process, and 3 to 4 it is the expansion process. At 4 point we can see the temperature is very low and pressure is also very low. So at 4 point we see that from 4 to 1 it is heating process. Refrigerant is absorbing QL amount of heat from its immediate space and converting into saturated vapor phase. So at point 1 it is saturated vapor state, where it again enters into the compressor. So friends, here we are concluding the vapor compression refrigeration cycle. In the next lecture we will complete the remaining part of this unit. Thanks. Have a good day.